Friends, after the discussion of the numerical 15.14, we are going to discuss about the remaining three numerical 15.15, 17 and 18. Already 15.16 already we discussed. Now, these three numericals are depends on the resonance and also what are the harmonic take place in the closed pipe and open pipe and also the string. Now in 15.15, a meter long tube open at the one end with a movable position at the other end shows the resonance with a fixed frequency source of 340 Hz. When the length is 25.5 centimeter or 79.3 centimeter, estimate the speed of sound in air at the temperature of the experiment. What it says that actually there is the experiment of the resonance tube like this way. In one tube partially filled with water. One open pipe is partially deep in this water. So this end is act as a closed end and that is the open end. As we place the vibrating coil at here. So what's happened? The sound waves are propagating in air medium and also some part of the sound wave reflected from the surface of the water and some are traveling in water medium. When the frequency of incident wave and reflected wave becomes the same, at that time the resonance occurs in this air column. In this air column. So here, this type of the resonance we obtain with a frequency of the fork is 340 Hz at two different length of a air column. First is obtained at 25.5 centimeter and second is obtained at 79.3 centimeter length of an air column. Here the A is present, so that is known as the air column. Clear this? Now, here the waves are propagated in a air column like this manner. The sound waves. Actually here the condensation and rarefaction take place, but that is easy to show on this type of the wave. So there is the incident wave, the reflected wave is propagated in opposite direction. When the frequency of the incident and reflected wave becomes equal, at that time the resonance occurs. And this resonance depends on the length of an air column. Right? For that purpose, for an air column in a closed pipe, the frequency of the nth harmonic Fn is equal to 2n minus 1 into V upon 4s. Now, for an air column, in a closed pipe, frequency of nth harmonic is Fn is equal to 2n minus 1 into V upon 4n. Here the n is equal to 1, 2, 3 and so on. That is the equation of the frequency of nth harmonic. Right? Okay. The first resonance occurs at the length L1 is equal to 25.5 centimeter. Right? Now, for first resonance, frequency is Fn1 is equal to 2n1 minus 1 into V upon 4L1. That is the equation 1. And for second time resonance, and for second time resonance occurs at another length 79.3. Frequency is Fn2 is equal to 2 into minus 1 V upon 4L2, equation number. Clear this? So both have the same frequency, that is the 340 Hertz, FN1 and FN2. So here we also mention this frequency here in equation 1 and 2. So both have the same frequency, that is the 340 Hertz, and is equal to also 340 Hertz. Equation 2, that is equation 1. Now comparing these two equations. Compare equation 1 and 2. Compare equation 1 and 2. Because the Fn1 is equal to 340 and Fn2 is also 340. Therefore, 2n minus 1, 2n1 minus 1 into V upon 4L1 is equal to 2n2 minus 1 V upon 4L2. We cancel, 4 cancel. Thus we obtain 2n minus 1, 2n1 minus 1 upon 2n2 minus 1 is equal to L1 upon L2. L1 and L2 are given 25.5 and 79.3. That means 79.3. That means the 1 by 3. Thus we obtain N1 is equal to 1 and N2 is equal to 2. N2 is equal to 2. Okay. Now for L1 is equal to 25.5 centimeter. The fundamental frequency F1 is equal to V upon 4L1. V upon 4L1. But F1 is given the 340 Hertz. Therefore, V is equal to 4 into 340 into L1 into L1. L1 is 25.5 centimeter. That means the 255 meter. 0.255 meter. Therefore, 346.8 meter per second. That is the speed of a sound wave in an aircraft. We can also find out the speed of a sound wave by other method. For L2 is equal to 79.3 centimeter. The first overtone or the third harmonic. The first overtone or third harmonic occurs. Or third harmonic. The frequency is F2 is equal to 3V upon 4L2. 4L2. There is also 340 Hertz. There is also 340 Hertz. Therefore, V is equal to 4 by 3. 4 by 3 into 340 into L2. But L2 is equal to 4 times of L1. Right? There is also a 3 times of L1. But L2 is equal to 3 times of L1. Therefore, 4 by 3 into 340 into 3 L1. 3 cancel. Again, we obtain 346.8 meter per second. That is the speed of a sound wave in aircraft. Actually, there is the experiment is in your syllabus to find out the resonance in 11th standard, right? Experiment, resonance tube. When the vibrating fork is placed on the this open cylinder. Open cylinder is partially dipped in water. Therefore, the other end is act as a closed end, and one end is open. Therefore, there is the closed pipe with one end is closed. When the vibrating pole is placed here, so the sound waves are propagated in a tube in air column. So this sound wave reflects from the surface of the water. When the frequency of incident wave and reflected wave becomes the same, at that time the resonance occurs. To find out this resonance, we have to slightly keep out this cylinder from the surface of the water. As the length of air column increases, for certain length we obtain the resonance. That is the experiment. For an air column in closed pipe, frequency of the nth harmonic Fn is equal to 2n minus 1 V upon 12, where the n is equal to 1, 2, 3. Here the frequency of the pole is 340 Hz. For given frequency, the resonance occurs at the two different lengths of air column, 25.5 centimeter and 79.3 centimeter. Estimate the speed of sound in air. For that purpose, here the first resonance occurs at the length L is equal to L1. L1 is equal to 25.5 centimeter. Therefore, the frequency is Fn1 is equal to 2n1 minus 1 V upon 4L1. That is 340 Hz. And for second time resonance occurs at length L2, 79.3 centimeters. Therefore, we take Fn2 is equal to 2n2 minus 1 V upon 4L2. That is also 340 Hz. Now we are comparing these two equations. So we obtain 2n minus 1 V upon 4L1 is equal to 2n2 minus 1 V upon 4L2. V upon 4L2. So here we simplify 2n minus 1 upon 2n minus 2 is equal to, we obtain the L1 upon L2. L1 is 25.5 centimeter, L2 is 79.3, that means is equal to 1/3. So as we simplify, we obtain the value N1 is equal to 1 and N2 is equal to 2. For the initial length 25.5 centimeter, the first resonance occurs. Therefore, the fundamental frequency F1 is equal to V upon 4L1. F1 is given, therefore we can find out the speed of a sound wave in the air column. Now, for second length 79.3, resonance also occurs. At that time, here there is the closed pipe, therefore only the odd harmonic take place 1, 3, 5. Right? So first resonance occurs at the length 25.5 centimeter, while the second resonance occurs at 79.3. Therefore, there is not a first for the fundamental frequency. So here there is the overtone. The first overtone or the third harmonic occurs F2 is equal to 3V upon 4L2. Is also 340 Hz. Therefore, speed of a sound wave V is equal to 4 by 3 into 340 into L2. But here the L2 is equal to 3L1. Because the next resonance occurs at 79.3, that is the 3 times more than the 25. Therefore, the speed of a sound wave we can also find out by using this equation 346.8 meter per second. Now the next numerical 15.17, a pipe of the 20 centimeter long. Right? The length of a pipe is given the 20 centimeter. That means the 0.2 meter. The pipe is resonantly excited by a 430 Hz source. The frequency F is given the 430 Hz. Will the same source be in resonance with the pipe if the both ends are open? The speed of a sound wave in A is 340 meter per second. So that is our F1. Now F is equal to 3 speed of a V is 340 meter per second. For a closed pipe, the first harmonic. For a closed pipe, frequency of first harmonic F1 is equal to V upon 12. Now speed of a sound wave is given 340 upon 2. Length of a pipe is given 0.2. Therefore, 425 Hz we obtain. That is the frequency of the first harmonic. But F proportional to F1, F proportional to the F1. And here F minus F1 is 430 minus 425, that means the 5 Hz. Right? This difference is very small. Is very small. This difference is very small. So the vibration of the source will produce the resonance in a closed pipe. Now here the F is given the 430 Hz and the frequency of the first harmonic we obtain, that is the 425 Hz. Right? Therefore, the difference between these two frequencies is, there is the 5 Hz, this difference is very small. Therefore, the vibration of the source will occur with the produce the resonance. Thus, vibration of source will produce resonance in a closed pipe. Resonance in a closed pipe. Again, what is given? A pipe of 20 centimeter long is closed at the one end. Which harmonic mode of the pipe is resonantly excited by 430 Hz source? Here the frequency of the source is given the 430 Hz. Length of a pipe is given 20 centimeter, that means the 0.2 meter, and speed of a sound wave in a medium is given 340 meter per second. If both ends are open, so resonance occurs. For that purpose, for a closed pipe, the frequency of the first harmonic F1 is equal to V upon 12. V is given 340 upon 2 into 0.2, that is the 425 Hz. We know that the given frequency is directly proportional to the harmonic, frequency of the harmonic. Therefore, F minus F1 is 430 minus 425, that means we obtain the 5 Hz. This difference is very small, thus vibration of the source, that means the 430 Hz frequency, produce the resonance in a closed pipe. Right? Now for open pipe. For an open pipe, the frequency of the first harmonic F1 dash is equal to V upon 12. V upon 12. So V is given 340 to L is 0.2. Therefore, we obtain F1 dash is equal to 850 Hz. 850 Hz. For open pipe, the other harmonics are 2F1, 3F1, 4F1. For an open pipe, other harmonics are 2F1, 3F1 and so on, which are greater than the 850 Hz. which are greater than 850 hertz. Therefore, no any frequency matches with the 430 hertz. Right? So, no any frequency matches with 430 hertz. So, resonance cannot produce in open pipe. So, resonance can't produce in open pipe. And also in open pipe, the fundamental frequency F1 is also 850 hertz. That is the very last of the source, frequency of the source. Frequency of the source is 430 hertz. Therefore, this source can't produce any resonance in a open pipe, because for the open pipe, the frequency are fundamental frequency 850, second is the 2F1 double of 850, third is taper of the 850. Therefore, the frequency of the harmonic increases. No any frequency matches with the frequency of the source 430 hertz. Therefore, this source can't produce the resonance in open pipe, only it can produce the resonance in closed pipe. Clear this? Okay. Now next 15.18. The two sitar string A and B playing the note ga are slightly out of the tune and produce the beat of the frequency 6 Hz. The tension in the string A is reduced and the beat frequency is reduced to 3 Hz. That means initially the frequency of the A and B, two wire of sitar, produce the beat 6 per second. Now the tension is slightly reduced in string A. At that time the number of beats produced per second are 3. If the original frequency of the A is 324 Hz, what is the frequency of B? So here the FA is given, there is the 324 Hz. We have to find out FB. So for that purpose, frequency of A is FA is equal to 324 Hz. And initial beat FA minus FB is equal to 6. Therefore, FB is equal to either 318 Hz or 330 Hz. Now the tension in string A is reduced. After reducing the tension, in a string, frequency of A is FA dash, which is less than FA, which is less than FA. Because we know that, what is the reason? The frequency is directly proportional to the tension. As the tension decreases, frequency is also decrease. Frequency is also decrease. Here the frequency decrease, tension decrease, therefore the frequency is also decreased. Therefore, the frequency of A is reduced after the reducing the tension in a string. Now, FA dash minus FB is 3 Hz. Is 3 Hz. So, FB must be 318 Hz. 318 Hz. Thus, FA is equal to 324 Hz and FB is equal to 318 Hz. Therefore, FA minus FB. FA minus FB is equal to 6 hertz. Here the tension in a string reduce. So FA dash minus FB is equal to 3 hertz. Therefore, FA dash is equal to 321 hertz and FB is equal to 318 hertz. So these are the frequency of the B. Frequency of the B wire is 318 hertz in both cases. Again, here the two string A and B playing the note Ga are slightly out of tune and produce the beat of the frequency 6 hertz. The tension in the string A is slightly reduced and the beat frequency is reduced to 3 hertz. If the original frequency of A is 324 hertz, and what is the frequency of B? So now the frequency of A is FA is equal to 324 hertz. Initially produce the 6 beat per second. Therefore, FA minus FB is equal to 6. Therefore, FB is equal to FA plus 6 or the FA minus 6. Therefore, a possible value of FB is 318 hertz or 330 hertz. Okay, now after reducing the tension in string A, the frequency of A is now FA dash. FA dash is less than FA because the F is directly proportional to the square root of tension. As the tension reduces, frequency is also reduced. Now, FA dash minus FB is equal to 3. So, as it consider the FB is equal to 330 hertz. So, at that time, the initially beat are possible, but after the reducing the tension in string A, the 3 beats is not possible. Therefore, the frequency of B must be 318 hertz. Because after reducing the tension in wire A, the frequency of the wire A is also reduced. There is the FA dash. There is reduced by the 3 hertz. Therefore, the frequency of initial frequency of wire is 324, and after the reducing, the frequency of wire A becomes the 321 hertz. Therefore, the frequency of the wire B must be 318 hertz. So, as a result, initial beat is 6 per second, and after tension in a string reduce, string A reduce. So, the beats per second are 3 after the tension in string A. So FA dash minus FB is equal to 3 hertz. Therefore, FA dash is equal to 320 hertz and FB is equal to 318 hertz. So friends, here the numerical of these chapters are completed.